Hi guys, and welcome to another Thursday, another webinar. We have a very interesting webinar today. It's on you might say, a little bit of an exotic topic, maybe not an everyday topic, but torsional loading of foundations. It's something that is very, very common in subsea structures, and it seems like an easy topic, but it's actually pretty advanced. So we hope you'll enjoy this. And before Kristian starts, who's of course our presenter today, I just wanted to let you know that next, I think it will be Wednesday or Friday, we will have a webinar with Benjamin from Dundee. Will come and present some work he's done on rock anchors. It's going to be very interesting, and I'll send out an invitation on this later today. So it's going to be Wednesday or Friday. So Thursday is a public holiday, so we decided to switch it a little bit. All right, but Kristian, please go ahead with the presentation.
Yeah, thanks, Sean. And let me share my screen. So, torsional loading of shallow foundations was what I am going to talk about. And as Jan said, it's an interesting subject because it's something that we don't normally consider for normal building foundations. There's usually not any torsional loading, but for various other types of foundations and structures, it is something that it can be, it's definitely relevant and maybe in some cases even important or critical. So, but it's not really a mainstream thing. It's not something you find in the standard sort of codes or textbooks or so on. So that of course makes it also interesting. So a brief outline: the effects of torsion is what we're going to look at, and what I thought could be done, but I'm not really sure about that. That's why I put a question mark. Is that could we introduce the effects of torsion by including another factor into the bearing capacity equation, what I call a torsion factor, which would be similar to an inclination factor. We could look at VT diagrams, and that's another way of characterizing, of course, the effects of torsion on the vertical capacity, and that would give us a reason to also talk about a feature of G3 that I don't think a lot of people really use, and that's the scripting interface. So it is possible to use, there is a scripting interface attached to G3, and I'll show you, give some indication of how that's used for basically generating VT diagrams, which is something that requires quite a lot of calculations, right? So, and you can do that in automated fashion with the scripting interface. And then this morning we had an email, so thanks for that, which was a really interesting email that pointed out a kind of an interesting little problem, or sort of something that is still a bit of a mystery, actually. Both, I think it's fair to say, to Jan and I, we spent all morning discussing it, but there is a solution, an exact solution for the undrained torsional capacity of a general rectangular foundation. And that solution can be relatively easily adapted to the drain case, except that this adaptation is not really, doesn't really work after all. So the question is why that is, and I'm not so sure I have the complete answers to that, but I'll definitely show that an equivalent, what I believe in is an exact solution for the drain case, is probably the exact solution. So anyway, the bearing capacity equation, and that's where we basically were 2 weeks ago in our webinar on the bearing capacity equation. So the standard bearing capacity equation applies to this kind of foundation here, general rectangular foundation, where the aim is to determine the maximum vertical capacity, and you may then have some horizontal loads and some bending moments as well. And they're taken into account by the horizontal loads by the inclination factors, the bending moments via the effective area approach, so that they generate an eccentricity, and shape factors to take shape, so deviations from the plane strain strip footing case into account. And I think the conclusion 2 weeks ago was that the bearing capacity equation is pretty good. There are some issues. There are some that I just wanted to sort of just raise again. The bearing capacity factor in Ghana, first and foremost, is I've said this more times than I can count, and I'll say it again. The exact solution is actually available. The exact in Ghana is available. Chris Martin's in Ghana from 2005, and that is really the one that should be used. That is a very sort of low-hanging fruit in terms of modifying the bearing capacity equation. There were some issues as well with the superposition, not a huge issue. It leads to conservative solutions, but they're not that much conservative. Incline loading, also potentially some issues with the common expressions found in the codes, not really taking into account failure by sliding, so you have to check that separately, which I don't really think should be necessary. Eccentricity, some minor issues, and shape as well. The shape factors, what do they really take into account? Is it just the geometry, or is it more than that? Is it also the fact that the friction angle is not constant, that we have one friction angle under plane strain conditions and different friction angles for general three-dimensional states of stress, depending on what stress state exactly you have at a given point in your soil. There's disagreement about that. So that's a bit of a sort of a point that is not exactly very clear, but something that is quite clear and something that is obviously missing is the sixth degree of freedom, namely torsional, the torsional component. So you could, in principle, have a torsional moment up here, how do you take that into account? And yeah, so and where would that come into to play, a torsional moment? Well, for these sort of large offshore structures, I've been told that one of the load cases is to consider is the case where a trawl or a fish net gets caught at the corner of a structure like that, and that of course generates vertical force, and could also be some uplift. I think that comes with this trawl load case as well, and then some torsional moment if you refer to the center of the foundation. So that's one example anyway of where torsion comes in. So a possible modification would be to include torsional factors, TC, TQ, and T gamma, following the general sort of scheme of the bearing capacity equation. And so that would be a possibility, and that's what I'm just going to have somewhat of a look at. And I'm going to refer to a surface foundation on sand. So no Q term and no C term, so we are left with this sort of, we call it the modified bearing capacity equation, modified by this torsion factor T gamma. And I'm going to do one more modification to the N gamma. So this is the plane strain N gamma, you could say, and then we multiply on the shape factor to get the N gamma for the factor for a general foundation. But there is the thing with the friction angles as well. So I'm going to refer to a new N gamma, I call it N gamma star, which would be a function of the B on L, and then also of the plane strain and triaxial compression friction angles that go with this model that we call the FASD model. And just, we have a separate webinar on that, so there's much more details on that on that webinar that you can find on our YouTube channel. But just to emphasize again that the friction angle does actually vary quite considerably depending on the stress state. So say between triaxial compression and triaxial extension. These are data of Lada and Wang for loose, medium, and dense sand. true triaxial tests, this is the B ratio here. So some ratio between the principal stresses, where 0 corresponds to triaxial compression, 1 is triaxial extension, and plane strain is then somewhere in between. And you can see a pretty significant, or some definitely variation of the friction angle, especially from triaxial compression and then up to sort of other stress states, with the triaxial compression being quite a bit lower than, say, at plane strain. There's lots of empirical correlations between these two angles, the plane strain and the triaxial compression angle. Some of them are shown here. This is 1.12. This is what I've used here, one that I think fits definitely the LADA data really quite well. There's some that say that it should be a function of the relative density or the density index as well. These results don't really seem to indicate that, but there's definitely a difference, and that difference can be taken into account with the so-called FASD model, the friction angle stress state dependent sand model, which is a combination simply of the Mohr-Coulomb criterion, so Mohr-Coulomb for the plane strain angle, and that would give then a friction angle that's too high in triaxial compression, so you cut that corner off with a Drucker-Prager circle. And somewhat surprisingly, maybe this very simple kind of composite model really fits data, the experimental data, really well. This is for lattice data again, and a ratio between the two angles of 1.12. So that, I think, that's what I'm going to use here, in addition to Mohr-Coulomb, just to have a look at Mohr-Coulomb as well, and then so just to make that clarification. And then, so this torsion factor would be one way of characterizing the effects of torsion on the vertical capacity, but another way would, of course, be to construct the VT diagrams. So to identify the combinations of vertical force and torsional moment that lead to failure. So if we draw it like this, so V out here and T on the y-axis, well, we know that we have a point here on this diagram, because that's just the pure standard vertical capacity. We know that we pass through the origin, because what torsion is a kind of a torsion, of course, introduces or induces shear at the base of the foundation. The shear strength of frictional materials are proportional to the normal force. So the normal force is in this case generated by the vertical force. And if there is no vertical force, well, then there is no torsional capacity. And so we have some sort of envelope that would probably look like this. And then we can sort of look at, let's say, just from a purely mathematical point of view, the asymptote of this envelope down here at the origin. And the idea that there is some sort of limiting torsional capacity, again, in analogy with the sliding limit that we have for VH loading. So for a combination of horizontal and vertical loading, we know that we have a limit here. It's just basically the basic Coulomb frictional limit, where the horizontal force, of course, can't exceed the vertical force times tan phi. It's similar, we would expect, when it comes to torsion, which is also kind of manifests itself in shear at the end of the day. And so that's what we looked at some time ago. What would this limiting torsional capacity be? So basically, for a vertical force tending to 0, what is this torsional limit? And so we considered this type of situation, a general rectangular foundation, B by L, some normal force generated by the vertical force, or some normal stress generated by the vertical force, and then what is the maximum torsional moment? To find that out, you postulate a mechanism of failure, so a simple rotational mechanism, and then there's actually also an uplift due to dilation if you use standard limit analysis. And you can then equate the internal and the external rates of work, and then you will find this solution here. So you'll find a maximum torsional moment that can be expressed in this way here. So it's proportional to V, and then it also involves the geometry, the L and B ratio, and it's proportional to the friction coefficient, or tan phi. Now, if you look at this thing in under the square root times the tan phi, that's kind of you could say a friction coefficient. I call it the torsional friction coefficient, mu t. So then you can express this solution as in this way here. So the t divided by the width is just the friction coefficient times the vertical force, which is very analogous to what we have with the sliding limit. So that seemed to make sense. I should say, though, that the real reason we started to look at this in the first place was that we were contacted by some OPTUM G3 users, or by one OPTUM G3 users, who informed us that our solutions with torsional capacity were off by about a factor of 2. And we, of course, we're not happy to hear that, especially not a factor of 2. That's always a kind of a nasty number to be off by. So we had a look at that, and that's how we came up with this solution. The factor of 2 comes from a comparison to the undrained solution, which is this solution here. So in the undrained case, well, you have the torsional capacity, so the normalized torsional capacity given by this expression here. It's a lot more complex than the drained, but this is how it is. This theta here, I forgot to put, that is arctan to B on L. So what you see here is you have some area times SU, which is kind of like the maximum shear force, right? So, and that you could say is equivalent then to the vertical force times the tan to the friction angle. So you can quite easily, and in a quite, I think, at first glance anyway, very reasonable way, adapt this undrained solution to the drain case. So then it looks like this. It turns out, though, that that there's quite some discrepancy between these two solutions. So this is the drain solution that I showed before, and then this Murph et al. Adaptation, the drained adaptation from the undrained solution. And that is, if you look at it, more or less a factor of 2. It's actually not quite a factor of 2. Here's the ratio between the two. So it's a factor of 2 for the limiting case of a footing with a 0 width, but it's a little less than 2. So it's not just a factor of 2 that's at play here. So the question is, can we trust this drain solution? And I think we can. We can definitely also trust the Murph et al. Solution. That seems to also be an exact solution if you definitely compare with runs, with G3 runs, with numerical analysis that I just did this morning here. So they're not exactly as accurate as I would like them to be. The undrained solution is very good. The drain solution is a little bit less good, but it's a lot better than it actually looks. There's an error of about 3 to 5%. The undrained is less than 1%. And we know that drained analysis tends to be more difficult than undrained. So I think this is very much as expected. And also just to say that these solutions were computed on sort of a domain like this and with a mesh like that. So most of the vast majority of the elements are wasted here because all the action is at the interface here. So that also explains this sort of slight discrepancy. But I think there's every indication that this drained solution is exact. So that's the torsion limit. And but then if we return to this torsion factor that we could include into the bearing capacity equation, what would be the requirement? Well, it would have to be 0 once we are at this torsion limit here. I think that's a very reasonable requirement, right? So, and that can be achieved by postulating a sort of a torsion factor like this, where this quantity here is sort of the normalized torsion capacity. It's 1 when you're at the limit. So the factor becomes 0. And again, that's analogous to the inclination factor that I advocated some time ago, a couple of weeks ago, 2 weeks ago, that also automatically incorporates the sliding limit in contrast to what you see in most of the code equations. So that can be done relatively easily. And just to sort of emphasize this thing about about obeying the sliding limit. So this is V versus H, code expressions, and then the alternative expression that I just showed you, and OPTUM runs in blue with blue squares here. And there is an issue down here, right? You shouldn't exceed the torsion or the sliding limit in this case, or else you have to check it separately, which of course is not necessarily a big deal. But ideally speaking, it should, I think, be incorporated into the inclination factor in the same way this thing here should be obeyed as well, the torsion limit. So this is one possibility. Another possibility is like that, take the bracket, put the brackets out here and the M there. And yet another possibility, combination of the two, and that turns out to, I think, be necessary if you want to fit sort of the results. So two factors, M and N, where you would hope, and that's what sort of preliminary results indicate, that one is a function of the friction angle, and another is a function of the geometry. So this would be a possibility, and then you can easily, if you use that up here, then convert that into a VH diagram expression for a VH envelope like that, and then the runs, the actual numerical results would determine these two parameters to those. So that's what I tried to do, and I'll show you the results a little bit later. But just back to the VH or the VT diagrams, how do we actually determine those? Well, that can be done in many different ways. One way would be to first determine the vertical capacity, so the standard vertical capacity, which is a normal standard limit analysis with respect to the vertical load, assuming no torsion at all. So that gives you an upper limit of the vertical load, and you would like the lower limit as well, which in principle is a limit analysis with respect to the vertical force pointing in the opposite direction. That's not really necessary here because it's obvious that it's at the origin here. But if you have a foundation with some finite uplift capacity, that's how you would do it. So you have this range of V, the minimum to the maximum. And then what you start doing is you can fix the vertical load at some level less than the maximum vertical load, and then do a limit analysis with respect to the torsional moment. That would give you a point here, and then if you move right to left, well, another V that's a little bit smaller, and then another limit analysis with respect to the torsional moment. And then once you have enough points, then basically you have your VT diagram. And that's what I wanted to, I don't have that completely ready, but let me just open this file here. I did this manually. So that's what I wanted to just to show you some mechanisms. So this is a huge file that takes a little bit of time to load. There's 20 or so stages in this file. So here we are, and so this is then the first problem, that to determine the maximum vertical load. This is a footing that is 4 by 2 meters, I think. Yeah. And so you do that, no standard limit analysis for vertical capacity, and then you start basically generating the other points on the VH diagram. So in this case, the vertical capacity was 1220. So you apply a vertical force that's a little less, 1156 in this case, and then the red forces here are the forces that generate the torsional moment. We are not able to apply a torsional moment directly at a node. You'll have to sort of do it in this way here. And then you go down. I set up 2 stages. I have all the results, but then when the purely vertical capacity, that sort of looks the failure mechanism as expected, torsion, but you don't see very much effect. you see that when it comes down to when you go in the diagram now, and so when we get close to this left edge here, to become more dominant, and that's of course how it should be. Good. So you can do that, and I did it. I found the maximum V, and then I manually put the fixed 756 and whatever down to 0, and that can be done, and it's not too tedious to do. But then once you're done, you find out that your domain is not large enough, or your domain is too large, or you want to change something and then you need to basically start from scratch, which is of course not exactly what you want to do. So as an alternative to that, there is the, and let me just close that. Oh yeah, I need to start it up again. As an alternative phase, and through Matlab, and the first thing you do when you start up the program, like that, is that you need to go here to remote control and start the remote control. You're now able to remote user interface via Matlab, and a script here. I'm not going to go through all the details and share this script after, those of you who are interested. So I have here with some parameters for the dimensions, the material parameters, so on, stage settings, the number of elements, start elements, and so on. And then I call actually first calculate the V. Let me move to that script. So this is where the model building really starts. So I first create a box, and we can try to run it. So I will just run this script. It's free underscore, and then this is what happens. Here's my box. Here's my box, and with the rectangular sort of domain on top as well. Then I want this. We move. If we want this cross at the center here. It's a bit annoying. Let me just see if I can change that so we can see. Create some materials, apply materials, and so forth. First create the material, specify the materials, and then we apply those materials. So we've selected now, and now the soil material has been applied. And let's see, and eventually you run the problem, and it runs the problem, and you can then also, of course, access the results. In this case, you want to extract the load multiplier. That's the only result you're really interested in. But if there are other results, they're available as well. And then with this, but just to say that then the actual torsional begin. You leave that, you can leave it overnight, or matter how many stages you want, you have enough time. So, and just show you, if you go to, and then there's a folder, if you have the program installed, called OPTUM, and then the OPTUM G3. There's a folder called Matlab examples, where there's a range of examples for different problems, so that should have sort of a feel for how to set up, how to use these commands, this space. It's one of those things that's kind of, it's learning by doing, I think. My document folder, There's documentation about all the different commands, classes, and so on. Here they are. Box, for example, how does that work for creating a box? And also important is material parameter document that has the material parameters, what we call the display. The display names are the names displayed to the interface, but those are not necessarily the net you would use when it comes to defining the materials in the scripting interface. So for example, for more Coulomb, there's a uppercase phi, that is of course the Greek lowercase phi that is displayed in the user interface. So it should be something that is relatively straightforward to get started with the examples we have. So if any of you are interested in that, I think it's worth giving a go, especially if you're running parametric studies or these generating these types of diagrams here. So what I did was I did 3 runs for this footing with B on L equal to 1/2. And first the more Coulomb, I call that, and then I have phi PS, which is 1.12 times 30, I think it's 33.6. Another MC analysis, and the problem with more Coulomb is, of course, always the 3D, which friction angle should you use, compression or the plane strain, and it sort of depends. And in this case, it turns out that it's the plane strain that is, if you compare with the FASD model, the results are much closer to more Coulomb with plane strain. But of course, you didn't know that before. So, but that's how it is in this. And normalized form, just to show you that all the results sort of tend to the torsion limit, which they should. And also finally, to just show the fast results, and those are the ones that are really of interest. The friction limit, the drained solution, torsion limit over here, and then the Murphy-L adaptation, which is violated. So again, an indication that this drain solution is the way to go. It's not a huge difference really if you look at things, and if you try to do the curve fit that I before, well, that tends to be kind of closer to the Murph in this case. So that's really what I wanted to say about this. So I'll be happy to take any questions if there are any. And let me see.
I think there are no questions, Kristian, but an extremely good presentation.
Okay, well,
Yeah.
The area between sliding and bearing is very small. I'm assuming you're referring to the to this slide here. So yeah. So the code, the east inclination factors are such that they kind of imply a violation, which and again in the big scope of things, green and red lines are not terrible fits to the actual, let's say these are backed solutions, the OPTUM solutions. This is G2 with the large upper and lower bounds. So yeah, no, I mean, it's not as if it's orders of magnitude. It's just that there is a limit, right? And you might as well into the inclination factors rather than having to check everything is okay as well. But you cannot get past the black line, and I was quite surprised when I started looking at the codes that those inclination factors actually, if you look at the NXD of Eurocode 7, this is the inclination factors are what is given, and it doesn't say anything about having to check for sliding. That's in another part of the code. But yeah, so I think it would be preferable if that sliding limit was embedded in the inclination factor, and same for the torsion factors. If that's the way you want to go, I should say I'm not so sure this is really the way you want to go. I think getting a hold of these torsion factors is going to be probably too complex, and you might just want to set up your problem and apply the forces and do the limit analysis, and then maybe do some parametric studies. I think that would definitely be much easier, and I think at the end of the day also much more reliable.
How long, Kristian, how long time did you spend on running through those points or generating those once you had the script set up? What was the computational time on generating the VT diagrams? Approximately.
I'm not sure. So this was for these that I showed here. That's 20 points with 10,000 elements and 3 adaptivity iterations. So how long does it take? A couple of hours, I would think, something like that.
Yeah.
Maybe a bit less. Depends, of course, how many elements you use. So these drain calculations are known to be fairly difficult, requiring quite a lot of elements, and probably maybe even more elements than the 10,000. You can see there are some wiggles in the curves here that you would expect things to be smooth, of course, but so maybe you would want to go for 20,000. I don't think it would make a huge difference. They would just be smoother.
Yeah.
And even 1,000 or 5,000 would give you something that is quite close to this, I think. So it's something that can be done relatively quickly.
Mm-hmm. We talked earlier today about the bad fit, about using the undrained expression and substituting the sigma times tan phi for the shear force. Did you get closer to that? Why the?
Why? Yeah, I mean, it's a good question, because as I said, it seems like a very legitimate and obvious adaptation to do, right? It's something that would work, of course, when it comes to pure sliding.
Yeah.
And so why isn't it working here? And I can't answer that question.
I guess the only thing that's changing is the stress, right? I mean, for a fixed friction angle, so it must come down to the normal, the stress in the normal direction.
Yeah. We would have to have a look at the shear stresses there at the interface and see what they are like in the 2 cases. So, but that's all I can really say. The analytical solution there that I showed is strictly speaking, it's an upper bound solution as well. So there was the possibility. I don't think that's a real possibility, but there was the possibility that it was just too high. It was just not a very good upper bound. But the mechanism, I can't see any real other sort of plausible mechanisms than this rotational one, I have to say. And the G3 analysis seemed to indicate that, yeah, I mean, it really is quite a good solution. So, and I would think I would put not maybe my life savings, but let's say half of them on the fact that this is exact.
Yeah.
And I think there was another question for the torsion. Yeah, so this issue with the torsion versus the sliding limit, how things look, how the actual VH diagram or VT diagram in that case looks. You can see that this limit actually, it's quite different in the two cases, because in the sliding case, the points here approach the sliding limit for quite a considerable V, whereas in the torsional case, it's only really down towards 0V that we approach this limit. So it is a limit that is the limit, but it doesn't really have the same kind of, you could say, it doesn't come into play in as obvious a way as in the sliding case. For this example here, I mean, that would, I strongly assume, be problem dependent, exactly the shape of these failure envelopes here. So yeah. So once you make the VT diagram, how do you enter its effect on calculating the bearing capacity of the foundation? Yeah, well, so if it's a question of the effect of torsion on the vertical capacity, then you have it directly from the diagram, right? Whatever torsion you have, well, you have some reduction, you could say, in vertical capacity. So and these VT diagrams here, you can then convert those into a factor, what I call the T gamma. I mean, it's sort of two sides of the same coin. It's just rearranging things. So whether you operate with this one here, if you insert that expression into here and then rearrange things, well, then you come to the VT diagram. So it's the same. The VT diagram it gives a much better understanding, of course, of what actually happens, but it can be converted into a factor if you want to do that. Yeah, how to generate torsion in the analysis. So I have done it in this way here by a force couple. You could do it by a single force, I suppose. You could do it by the forces pointing in the direction of the length. I mean, it doesn't really matter as long as it's a torsional moment. Then that's what matters, and you could do that in an infinite number of ways. Ideally speaking, you'd like to be able just to apply a torsional moment at a point that's not possible. Maybe it'll be possible in the future. I think so. It's something that we've been working on for bending, and we might as well include torsion into that as well. So yeah, the influence of shape on the torsional capacity. There's the influence of shape on the limiting torsional capacity. Where was that? Was over here. So that's basically shown here. So the more we tend to a strip, actually, I mean, it's 0.5 for a strip versus 0.7 for a square foundation. The relative torsional limiting capacity. So it's not a huge difference actually. But but there is, of course, an effect on the exact shape of the foundation, and it'll also there'll also be a difference in the shape of the VT diagrams, but not huge. So, but I don't have results actually, unfortunately, to give you a more concrete answer than that.
That's fantastic, Kristian. Maybe we should call it a day.
Yeah, let's do that.
Yeah, thanks for, I must say, a fantastic presentation. Very, very, very interesting. And nice. My video was lagging a bit when you presented the Matlab. I don't know if that was for all participants, but we'll have a look at the video, and like Kristian said, that this script we went through will be, I'll send it out to you guys so you can try to run it. So if you have Matlab, it's really easy. It's basically starting up G3, then pressing a button and running the script, and everything just goes very nicely. Yeah, so next Wednesday, next Friday, we continue on offshore topics with rock anchors. We hope to see you there. Very interesting to hear Benjamin's presentation. We're looking forward to that anyway. And yeah, so have a great day tomorrow, and a nice weekend when you get there.
Yeah, thanks for attending, and hope to see you next week.
Yeah. Cheers.
Bye.